It's an absolute pleasure to be here tonight, and thanks all for coming out to a first ever Machine Learning at Uber meetup. I've been at Uber for approximately 3 years now, and I'm part of the data science platform leadership group. So what are data science platforms all about? I'm sure that many, if not all of you, have prototyped, productionalized, and monitored machine learning or data science models at scale. And I'm sure that you have encountered multiple pain points throughout that process. Be it, for example, that your data volume was extremely large and you had to build your own data pipelines because the infrastructure was not supported. Or perhaps that you needed a lot of engineering overhead to go from prototype to production. Or perhaps you wanted to automatically monitor your models and quickly identify if there were any data quality degradations that were happening. So these and many other problems are key and the mission of the data science platforms, where we build products where Uber is the customer. What we're hoping to accomplish here is heightened efficiency within our data scientists and machine learning engineers. Of course, data science platforms are not a silver bullet, and building these might take time, perhaps a couple of months and quarters. However, we do believe that this is an ROI positive investment if we have multiple use cases across the company or the organization that overlap sufficiently to make abstraction viable. So not surprisingly, with the many different data science and machine learning problems that we're solving here at Uber, we have multiple different data science platforms that we have identified and have been building out over the last quarters and years. Unfortunately, due to time constraints, I can only talk about 3 of these platforms today, but I'm happy if you find me after the talk to talk about the other data science platforms that are currently in the works. Of course, at the heart of machine learning sits our machine learning platform called Michelangelo. I will also briefly touch on our forecasting platform. As you've already heard from Chintan, forecasting is a very integral part of our Uber ecosystem. And then finally, I'll conclude by looking at the anomaly detection platform, which allows us in real time to find anomalies within time series and to make monitoring just a click of a button. So let's start off by looking at our machine learning platform, also internally known as Michelangelo. By the way, the team recently published a blog post, so I encourage you to check out our engineering blog post after this talk, which has much more information and details about this topic. In a nutshell, what makes Michelangelo special is that it is heavily integrated with our infrastructure, our data sources, as well as our business operations, and that allows anyone to build machine learning models pretty much at a click of a button. You can bring your own IPython notebooks, and you can then productionize them extremely easily. So really, Michelangelo provides an end-to-end machine learning workflow at scale, starting from getting and training the models to then evaluating them. At the bottom right, you see one of our feature report cards that the data visualization team internally built out. Then, of course, deployment at a click of a button, making predictions, and then automatically determining if any degradations might occur. The current scope of the Michelangelo platform spans both traditional machine learning as well as deep learning methodologies. It goes from supervised to unsupervised techniques, and recently the team has also started to work on semi-supervised methodologies. Of course, with our real-time nature of our business, moving in a very complex ecosystem that is ever-changing, we're also very interested in developing online learning models. Since the platform has been launched approximately a year ago, dozens of teams have been building on top of it and deploying and prototyping models. This ranges everywhere from our autonomous vehicles, pricing, ETAs, and other marketplace examples. So let's delve deeper into one of the examples that I want to share with you today from our colleagues in the Uber Eats domain. This team has built on top of our machine learning platform an estimated meal delivery time. This comes into play in 2 forms within the Uber Eats app. First, prior to you ordering a meal, and then afterwards with a revised and more accurate estimated time to delivery after you put in the order. This is a very complex endeavor to be estimating this time because there's so many different steps involved. This starts with the meal preparation time, which is obviously dependent about how many people are currently in the restaurant, what the staffing looks like, etc. This then obviously needs to fall down into ensuring that the driver courier partner arrives on time, finds parking, walks up to the restaurant, picks up the meal, drives to the destination, again finds parking, and delivers the meal. So many, many different steps involved here. The team is currently using a gradient boosted decision tree with various different features, of which I'm listing here a couple. These are not surprisingly a mix between historical and real-time features. For example, what was the recent meal preparation time for that restaurant? And then obviously there are some geospatial aspects as well. Where does the pickoff and drop-off happen? Let's move on to our recent extension of this machine learning platform, which lies within our natural language processing domain. Natural language processing is really a cornerstone within our machine learning ecosystem. There are so many use cases within NLP at Uber that I actually ran out of space on this slide. So I prioritized them with the various different items that we see here in the green column. This starts off with safety. We want to identify and resolve any safety incidences as quickly as possible. And you can imagine that NLP here is a big aid in this endeavor. This continues with driver assistance, for example, for driver onboarding, when driver partners have questions during this process. This continues with our communications. We recently launched an in-app experience that allows riders and driver partners to directly connect and chat via the app. This circumvents the need to exit the app and use SMS or voice to connect. Here, of course, we can leverage now intelligence beyond that and provide suggested replies, similar as you might be seeing in audio Gmail. Finally, NLP also comes into play in sentiment analysis and search engine optimization, as many search engines, such as Google, for example, use natural language processing more and more. Needless to say, NLP is a very challenging problem, and I'm listing here a couple of the challenges on the yellow column. This requires, for example, models to integrate both text as well as numerical data. And also our data sources are very disparate and span multiple media. The example that I want to highlight here is a recent development within our applied machine learning group in collaboration with our customer support endeavor, which focuses on support tickets. And as the lead said, how we can have humans and machines come together in symbiosis to make the customer support experience better. In this case, we are utilizing machine learning and deep learning methods to classify issue types that customers have put into our system. And the graph here on the right-hand side shows the challenging, the easier and then more challenging ticket types that are coming in. And on the y-axis, you can see the model accuracy. The blue line, the dark blue line, is a random forest technique. And recently we have been modeling also using convolutional neural networks that you see in orange and light gray. Here you can see that deep learning models are clearly outperforming our traditional natural language processing models in terms of classifying and recommending actions of report tickets. So now you might be wondering two questions. Why not LSTMs? This is clearly a sequence problem. Well, firstly, we have found that LSTMs and convolutional neural networks are of equal performance when it comes to accuracy. The second main important thing is that convolutional neural networks are substantially cheaper, often multifold, than LSTMs. So the second question you might be asking is, how does one do CNNs for natural language processing? Well, here you actually use vectors that are typically formed of word embeddings, be it glove or word2vec, or perhaps even one-hot encoding. And then the other dimension, the one dimension is basically the various different words or characters that you have. And the second dimension are the vectors that are typically comprised of word embeddings. Then you utilize a filter that you slide over the various different rows, which can have various different sizes. And the remainder is very, very similar to what you would be using in computer vision overall. Let's move on to our forecasting platform. Forecasting, as we've already heard from Chintan, is a very integral part to our Uber ecosystem. But we have also many other forecasting use cases that span across Uber. This ranges from finance, which does goal setting, marketing that works on budget allocations, in particular for paid marketing spend, and finally engineering, where we have to do extremely accurate hardware capacity planning very well in advance in order to order the hardware and set it up in time. How is forecasting different at Uber? As was already mentioned in previous talks, we're here facing spatiotemporal problem sets. We often have to work in real time due to the real-time nature of our business. We're an extremely young company, so if you want to model things that are year-over-year occurring, we have very few data points available. We're also faced with extreme hypergrowth, both in the cities that we've launched originally in, and then also expanding very rapidly into the more than 600 cities that we have been now in. Finally, as you've seen from Chintan's talk, we are also extremely sensitive to various different external events, be it concert, holidays, or various different sporting events. So let me tell you a bit of an example about hardware capacity planning that is particularly important for high demand days, such as Halloween or New Year's Eve. Why is that important? Well, on the one hand, if you over-provision, you're incurring a large overhead cost. And this cost is substantial given the size and the number of servers that we have at Uber. Of course, if you under-provision, then we will not be able to serve our riders and driver partners in a reliable fashion. So doing this is extremely important. Now, what makes this problem challenging is that we're trying to model minute-by-minute demand and supply multiple months out. And for this, we have developed proprietary algorithms that are extremely effective and extremely accurate to do so. Let me finish off with the last platform that I want to highlight today, which is our anomaly detection platform. How many of you are on call currently? Not that many. All right, if you're on call, you probably know this is a very painful experience. First of all, setting up the metrics and the monitoring for it. This is a very time-consuming and often very manual process. Then also being woken up in the middle of the night, only to find out it's a spurious alert. What if we had a machine learning algorithm that allowed us to only provide the business critical metrics, and the rest is completely done independently by this algorithm? No more setting thresholds manually, no more waking up in the middle of the night to find out it was just a blip that nobody could take an action on. As a matter of fact, we have halved the system now for the last 2 years at Uber. And we have been using it across multiple different services. The core concept here is that we want to provide transportation as reliable as running water, as Walid said. So clearly we want to aim for 99.99% of availability or higher. This means that we can provide transportation where riders can rely on us to get to the airport on time, to their job interviews, or to their children's birthday parties. This also means that our driver partners can trust us that whenever they open the app, they can earn a living on this platform. So really, we need a self-healing system. So we have utilized standard time series techniques and also change point detection algorithms, and now also recently deep learning algorithms to make new cutting edge developments in this field. This is very much still an open research question at this moment in time, and for a couple of reasons. One is that we have over 500 million time series at Uber. You might ask, why so many? Well, this is a combinatorial explosion of the 600 plus cities that we have, the multiple app versions that were available on iOS, Android, etc. The second thing is that we have to detect things within real time. If we want to be at 99.99% availability, we just get over 1 minute of downtime per week. And finally, as we've seen, we have a lot of patterns in our metric, be it day of the week, week of the day, or special events that are happening. And let me tell you, if an on-call, you do not want to be woken up to find out that a Beyonce concert just finished. Misses are very expensive. As we've seen, this erodes the trust of our rider and driver partners. But also spurious alerts are equally detrimental to the health of our teams. So let me deep dive a little bit into the deep learning that we have been doing on this front. We've recently published 2 blog posts in this field. Again, I highly recommend to check those out after the talk. But I want to give a brief glimpse on the first one, which is around engineering extreme event forecasting at Uber using recurrent neural networks. What the team has done here is that they have used first a vanilla LSTM approach that is trained over a corpus of time series and then applied to all of the time series. The problem with this is that it didn't outperform the traditional time series techniques that we were using before. Now, obviously, with 500+ million time series, you cannot train an LSTM model for every single time series. That is just not feasible. So how did we circumvent this problem? Well, we built an automatic feature extraction module that took in features that are time series characteristics, such as you can see here on the left-hand side. And then we used an ensemble of these output features to then concatenate with the inputs and run over it an LSTM. And that gave us a 25% increase in our accuracy. So with that, I want to conclude, and I hope I could give you a bit of a flavor of the various different data science platforms we have at Uber, what kind of use cases we solve, and how we can help increase the efficiency of various different teams. Thank you very much for your attention.